So integration by parts, which we usually abbreviate as just IDP, we typically use on mixture integrals. When I say mixture, I mean a mixture of different types of functions. So something like x times e to the x. You have x to a power and then e to the x. Or something like e to the x times sine of x. Right, where you have, again, a mixture of things. You have two different types of functions, an exponential and a trig function multiplied together. Or you could have x cubed times natural log of x. Or you could have, those are kind of those are most of the types you have, really. I mean, there are other types, but this is kind of the big three of types you have, right, where you have some sort of either logarithmic or algebraic or trigonometric or exponential function. You have at least two of these types of functions multiplied together. If that's the case, integration by parts is one of the methods we might use. The other method we might use is U-Substitution. So let's look at some examples. So let's go straight to this one. Let's look at this example versus, So let's do this example, the integral of 1 over x times the natural log of x squared dx. So for this integral, it looks like we might do, well, so I'm always going to think, can I do a U-sub first before I try integration by parts? So I can try letting u equal the natural log of x. And oh yeah, du is going to equal 1 over x dx here. So I can rewrite this integral as, well, my 1 over x dx is going to become du. So, right. That's my du. And then I'm left with 1 over u squared. Well, that's going to be the integral of u to the minus 2 du, which is then u to the minus 1 over minus 1 plus c, which is then u is natural log of x. So it's natural log of x to the minus 1 minus natural log of x to the minus 1 plus c. Or preferably negative 1 over natural log of x plus c. Perfectly fine. So there's an example of a mixture, right? We have x to a power, we have natural log of x, where we used a U-sub. And then, let me change the previous setting here. One moment. It's like a little too bright on the board. Hopefully that's a little easier for everybody to see the board anyway. Versus this problem, the integral of x squared times the natural log of x dx. Now, if I try doing a U-sub, but u equal natural log of x, my du is 1 over x, that's not going to work out. But u equal x squared, my du is 2x, that's not going to work out. This doesn't look like it's going to work to do a U-sub. So I'm going to try integration by parts. And using the LATE acronym, which mostly all the time works to pick u, I'm going to pick u equal to the logarithmic thing. So I'm going to let u equal the natural log of x. dv has to be everything else. So dv is the x squared times the dx. du is, well, the derivative of natural log of x is 1 over x times dx. And then v, the antiderivative of x squared, is x cubed over 3. So then we throw it all into the formula, right? Our integral is equal to uv minus the integral of v du. So it's going to be u times v minus the integral of v times du, which is x cubed over 3 times 1 over x dx. And the whole point is that this integral now is simpler to evaluate, right? X cubed over 3 times 1 over x reduces to x squared over 3. Or I would probably write it as minus 1/3 the integral of x squared. bring the 1/3 out, x cubed over x is x squared. So then this is equal to the natural log of x times x cubed over 3 minus 1/3 times the integral of x squared is x cubed over 3. So I'll repeat, the whole purpose of doing integration by parts is to make this next integral you get in your formula, uv minus the integral of v du, that integral should be simpler. And sometimes you have to actually do some simplifying to make it simple. Let's go ahead and look at some more examples. Sure. Let's look at, say, the integral of x times cosine of 6x squared. In this case, it looks like I could pick a U-substitution. If I let u equal the insides of the cosine function, my du is essentially just x, right? It's really 12x times dx, but I can divide both sides by 12. So that 1/12 du equals x dx. So once again, right, that's going to be my 1/12 du. So my integral becomes the 1/12 du, and then the integral of cosine of u. Well, great, that's not terrible. The integral of cosine of u is sine of u. That's 1/12 sine of u plus c, which is 1/12 sine of 6x squared plus c. In contrast, this next integral is going to require integration by parts. So if we do the integral of x times cosine of just 6x, it looks almost the same, but it's very different. Because now letting u equal 6x wouldn't help us get rid of this x here, right? We'd still have some sort of x times cosine of 6x. We'd have or u over 6 times cosine of u, right? It wouldn't really change. So here we're going to try integration by parts. So again, looking at the LATE acronym, I don't have a logarithmic thing, but I do have a quote unquote algebraic thing. And again, algebraic thing. So when people write algebraic here, I like to write any power of x. That's what I think of for the a term. So do I have a power of x? Oh yeah, I do. I have x to the first. So that's what I'm going to let u equal. And then my dv is going to be everything else, which is the trig thing. So dv is going to be cosine of 6x times dx. I'll remind you, another way we're thinking about picking u and dv is you want to pick u so that when you differentiate it, its derivative is simple. If you pick u equal to cosine, the derivative is sine. It's not really any simpler. Cosine and sine are about equally complicated. Whereas x, the derivative of x is 1. That's definitely a simpler thing. So du is 1 times dx. And dv, so this is where those mini u substitutions we talked about earlier in class are going to be important. Right? I'm going to anti-differentiate cosine of 6x. I'm not going to be like, okay, integral of cosine of 6x. I'm not going to do the u sub for u equal to 6x and so on and so on and so on. I'm just going to be like, I know the antiderivative of cosine of 6x is sine of 6x divided by 6, or times 1/6. That's why we spent time. That's one of the reasons we spent time doing that earlier in the course. So now this is going to equal u times v. So it's going to be x times 1/6 cosine of 6x minus the integral of v du, which is 1/6 sine of 6x dx. Great. We know how to integrate sine of 6x. This is going to be x. I would probably write this as x over 6 times cosine of 6x. And the antiderivative of sine is negative cosine. So I'm going to have negative 1/6 cosine of 6x divided by another 6. Right? Because the 1/6 there is from there, and the 6 down there is from integrating sine of 6x and getting negative cosine of 6x over 6. And then simplifying just a little bit, this is x over 6 times cosine of 6x plus 1 over 36 times cosine again. I feel like I made a mistake here. I did. I made a small mistake, and that's okay, right? This should be u times v, and I wrote my v wrong, right? So that v there should be a sine of 6x. Sorry about that. But so here's how I knew I was making a mistake. I was about to get plus 136 cosine of 6x again. And typically when you're doing integration by parts, the pieces here are not really that similar. So that kind of said to me, I probably should have something different there. And I should. Right? That should actually be sine. So I really want to stress, when you have a mixture of things, meaning something algebraic times something trig, or something algebraic times something exponential, or something trig times exponential, right? When you have a mixture of things, different types of functions, you might either be using U-substitution, or you might be using integration by parts. And it's kind of a guess and check, right? You're like, and usually the first guess is, I'm going to guess U-substitution. And then I'm going to see, like, does there seem like a plausible U-substitution? If not, I'm going to go try using integration by parts. Let's look at another example. Yeah, let's go back to this one. Okay, so one more contrasting example. That's interesting. I never thought about that. So let's say I have the integral of x squared e to the x cubed. Well, this is definitely a u-sub. I can let u equal x cubed. Du is going to be 3x squared dx. 1/3 du is going to be x squared dx. So I can see my x squared dx, and that's my 1/3 du. This is going to be the integral of 1/3 du, and then the integral of e to the u. That's not too bad. That's just 1/3 e to the u plus c, which is 1/3 e to the x cubed plus c. On the other hand, we could say, what's the integral of x squared times e to the x dx? And that's a whole different ballgame. Still a mixture, right? Still an algebraic, or any power of x times an exponential. So this is also an algebraic, any power of x times an exponential. In this case, we're going to use integration by parts. So we're going to let u equal the thing that's going to simply differentiate. We're going to use late, right? No logarithm things, but we do have an any power of x. So u is going to be x squared. And du is going to be 2x dx. Dv is going to be e to the x dx. And v is going to be the antiderivative of the x is also e to the x. Great, so now my integral is equal to u times v, so x squared times e to the x, minus the integral of v du, which is e to the x times 2x dx. And now I get to use integration by parts again. Right? I still have an integral. It's a mixture. It's still an algebra thing, or an any power of x thing times an exponential thing. So I'm going to do it again. I'm going to let, now for this integral in green, I'm going to let u equal 2x. My du is going to be 2 dx. My dv is going to still be e to the x dx. And my v is going to be e to the x. So then, rewriting what this is equal to, we still have this x squared e to the x up front, minus, and then the integral of this is going to be all of the ultraviolet supervoodoo. So it's going to be minus, in parentheses, all of u times v, minus the integral of v du. So e to the x times 2 dx. Great, we know how to integrate that. So we're going to get x squared e to the x minus 2x e to the x. Minus a minus is plus, and the integral of 2 times e to the x is just 2 times e to the x. So that's how you do this problem. Again, right, sometimes you have a mixture and it's U-substitution. Sometimes you have a mixture and it's integration by parts. And yeah, I feel like this is probably a good opportunity to mention the tabular method, or what I think some people call vertical integration. So we'll say this now, and then we'll do some more examples later. But this is a good example to kind of show you that it works. Depending on some teachers, for some reason, are like, don't use tabular. I don't know why you wouldn't use it. It's super straightforward when you can use it. So here's when you can use tabular or vertical integration, which is really just a shortcut for integration by parts. So it's really just an integration by parts shortcut. There are three types of integrals it works for. It works for the integral of x to a nice power times sine of x. It works for, dx. It works for the integral of x to a nice power times cosine of x dx. Or it works for the integral of x to a nice power times e dx dx. Technically, you can make this a little more complicated. You could actually make it the sine of a multiple of x. So you have like sine of ax. You could have cosine of ax. And you can have e to the ax. That makes it a little bit more complicated. Okay. So let's do the one we have, right? We were doing the integral of x squared e to the x dx. And here's how it's going to work. You're still going to pick your u and your dv the same way. So u is still going to be x squared, dv is still going to be e to the x dx. But instead of writing all of this other stuff down here, we're going to make a table. I'm going to make a column for my u, sorry, for my, for u, and then I make a column for my dv. Okay, the u column starts with x squared. The dv column starts with e to the x. For the u column, so when we do integration by parts, after you pick u, then you find the derivative of u. And the thing is, we're going to find the derivative of u until we get to 0. We're going to find the derivative. So the derivative of x, which is why u has to be x to a nice power. Because like x to the third, eventually you keep taking derivatives, the derivative is 0. Any other type of function doesn't eventually have a derivative at 0. Only x to a positive integer power eventually will have its derivative be 0. So the derivative of x squared is 2x, the derivative of 2x is 2, the derivative of 2 is 0. And I do think you want to write the 0 so that you have enough columns. Sorry, enough rows. And then on this other side, and I know it's not going to seem very obvious here because the derivative and the antiderivative of x are the same. But on the dv side, you're going to do the antiderivative the same number of times. So the antiderivative of e to the x is e to the x. The antiderivative of e to the x is e to the x. The antiderivative of e to the x is e to the x. Great. Then we go over one and down one. So we go there, we go there, we go there. We multiply these together and we put a positive sign. We multiply these together, put a negative, we change, put a negative front, multiply those together, positive sign. So my answer here is that this integral is equal to positive x squared times e to the x minus 2x times e to the x plus 2e to the x. Let's see. Just like we found right here. So that's one example of the tabular or vertical integration method. We'll do a few more of those later, but I just kind of want to show to you now because this is a good example. Oh, you can do this other kinds of for. But so here's kind of the real reason why you would do this. This problem maybe isn't so bad to do integration by parts twice. But if you had to integrate like x to the fourth times e to the x, you'd have to do integration by parts 4 repeated times. Or you could do the tabular method, and it's super fast. So that's really why we use it, because when you have these problems where you have x to a higher power times sine or cosine or e to the x, the process is super, super repetitive. We don't want to spend our time doing all that. Okay. Let's take a quick journey to the side here. Some people had some questions about some even numbered problems from the homework, from the book. It seemed worthwhile. I'll take a look at those. And then we'll talk about even and odd for a minute. So let's look at this. Where'd you go here? Sorry. What's going on my table? Okay. Yeah, that looks all right. That looks all right. That looks all right. Oh, we'll look at that one too. So let's look at this problem before we do one more. Let's say I have the integral of x times the square root of x minus 1. This is not an integration by parts problem. It's not even a mixture problem, right? There is no mixture of different types of functions. You just have really extra powers. Yeah, there's the square root as well, but we don't really kind of consider that like one of the mixture categories. Here, I would definitely be trying a U-substitution. I would let u equal x minus 1. du would be dx. So then rewrite this as the integral of, well, my dx is du. Great, took care of that. My square root of x minus 1 is the square root of u. Great, took care of that. And what's x equal to? If I want to write it in terms of u. I know you guys know how to do this. Someone could type a thing in the chat. Thanks. Yeah, exactly. Somebody told me in the chat. Somebody else could tell me in the chat too if they wanted to. X is going to be, well, if I solve this equation for x, u plus 1 equals x. And again, this is an example of what's called a back substitution, right? There were leftover x's, we back substituted into them after we dealt with the things we need. Then we're going to distribute this square root of x. We're going to rewrite this actually as the integral of u plus 1 times u to the 1/2 du. And then we're going to distribute. U to the 1/2 times u to the first is equal to u to the 3/2. And u to the 1/2 times 1 is just u to the 1/2. So then we're going to integrate. We're going to get u to the 5/2 times 2/5 plus u to the 3/2 times 2/3 plus c. And then we're going to plug back in that u is equal to x minus 1. So we're going to get 2/5 times x minus 1 to the 5/2 plus 2/3 times x minus 1 to the 3/2 plus c. Not a terrible question. So what I'm trying to kind of show you all is that you really kind of have to be willing to try anything, right? I mean, sure, there are kind of guidelines about when you should use a U-sub, when you should use integration by parts, but really you have to kind of be thinking, okay, I have all these tools at my disposal. What seems like the best thing to do? Let's look at another example. Yeah, let's see. The integral of, what have I got here? E to the negative x, from 0 to 1 of e to the negative x over the square root of e to the negative x plus 1. And again, just for clarity's sake, I would not classify this as a mixture problem. So the only really one type of function I have is exponential functions. So I'm probably going to try a U-sub. I'm going to let u equal the stuff inside the square root. So u is e to the negative x plus 1. And my du is negative e to the negative x times dx. Great, that means negative du is positive e to the negative x dx. So there's my negative du. Oops, pen on the finger. Not to put you guys off. I just want to show you the terrible, look at that. It's awful. I hate it. Yeah. Green pen on my finger. Sorry, let me end up putting red pen on my face. That'd be really great too. It's really like on the nail there. It's nice. Paint my nails with green pen. It'd be really lovely. It would not be really lovely. It'd be really gross. Okay, so this is going to be the integral of negative du over the square root of u. And I think we should change our limits of integration. So if x is equal to 0, u is going to equal e to the negative 0 plus 1. E to the 0 is 1, 1 plus 1 is 2. Great, so my lower limit's 2. And if x equals 1, u is going to equal e to the negative 1 plus 1, which is really not anything else you can do with that. That's just e to the negative 1 plus 1. Okay, it's not pretty. Sometimes the integrals aren't pretty. So I'm going to rewrite this as the integral from 2 to e to the negative 1 plus 1. Sorry, the negative integral of that. Interesting here. Of u to the 1/2, u to the negative 1/2. Now, here's something you might not know, but 2 is actually bigger than 1 plus e to the negative 1. Right? E to the negative 1 is 1 over e, which is definitely smaller than 1. And 1 plus it is definitely smaller than 2. So you don't have to, but you could. Actually, let's not. I was going to say you could rewrite this as the positive integral from e to the negative 1 plus 1 to 2 of u to the negative 1/2. But you don't need to do that. You certainly can do that if you want to and you recognize it, but I don't think we need to spend our time thinking about that. Let's just integrate it. So we're going to get negative integral of u to the negative 1/2 is u to the positive 1/2 divided by 1/2, which is like multiplying by 2, from 2 to e to the negative 1 plus 1. And so then we're just going to get negative 2 times the square root of e to the negative 1 plus 1 minus negative 2 times the square root of 2. Kind of gross. Not my favorite problem ever, but it works. Let's look at a similar one. Now I'm going to do this one slightly differently. But it's a very, very similar problem. Let's look at this integral of e to the 2x over e to the 2x plus 1 dx from, again, 0 to 1. Here I'm going to do it without changing the limits of integration. So often, if I feel like changing the limits of integration is kind of a giant pain, which it's not here, but let's pretend it is, I often do the indefinite integral on its own. So I might just say, okay, I'm going to do the indefinite integral of e to the 2x over e to the 2x plus 1 dx. I'm going to do a u sub. I'm going to let u equal the denominator. My du is going to be 2 times e to the 2x dx, and then divide by 2. So 1/2 du equals e to the 2x dx. So then this is going to become the integral of 1/2 du. Right, there's my 1/2 du. And then I'm going to have a 1 over u. Great, we know how to integrate 1 over u. That's going to be 1/2 the natural log of the absolute value of u, which is then 1/2 the natural log of the absolute value of e to the 2x plus 1. You could drop the absolute values if you wanted, since the absolute value of e to the 2x plus 1, e to the 2x plus 1 is always positive, but you don't need to. So this is going to be, so then what I'm going to do is be like, okay, I know how to integrate this. The integral of this is 1/2 the natural log of the absolute value of e to the 2x plus 1 from 0 to 1. Then I plug in the 1, I get 1/2 natural log of e squared plus 1. Just plugging in 1 for x. Minus, I'm going to plug in 0, and we get 1/2 natural log of e to the 0 plus 1. And I would probably simplify this. I'd probably factor out the 1/2 and I have natural log of e squared plus 1 minus natural log of 2. Or if you really want to simplify it further, you could go 1/2 natural log of e squared plus 1 divided by 2. Like that, if you really wanted to. So with definite integrals in U-sub, you kind of have a choice. You can either do the U-sub and change your limits of integration, or you can not change the limits of integration, do the integral first, and then plug in your limits of integration. And that's actually kind of what I do for integration of parts problems where you have definite integrals. So let's say I want to find the integral from, say, 0 to pi of, let's do x squared times cosine of x over 2. It's going to be a little bit interesting. So I will mention this is definitely an integral you could do tabular for. So I'm going to be like, all right, I know that the integral from not from anywhere. Let's just do the tabular thing. So tabular, I'm going to let u be x squared. And then all the derivatives are 2x, and then the derivative of that is 2, and the derivative of that is 0. And for my dv is going to be cosine of x over 2. So here's where we have to be a little extra careful with our tabular method. The antiderivative of cosine is sine. The antiderivative of cosine of 1/2 times x is sine of 1/2 times x divided by 1/2, which is multiplied by 2. And the antiderivative of 2 sine of x over 2 is going to be negative cosine of x over 2 multiplied by another 2. So 2 times 2 is going to be a 4. And the antiderivative of negative 4 cosine of x over 2 is going to be negative 8 sine of x over 2. Because if you go back up this way, if you take the derivative of this, the derivative of negative 8 sine of x over 2 is negative 8 cosine of x over 2 times 1/2, which is negative 4 cosine of x over 2. And the derivative of this is negative 4 times negative sine of x over 2 times 1/2, which is positive 4 times 1/2, which is positive 2 times sine of x over 2. And the derivative of 2 sine of x over 2 is 2 cosine of x over 2 times 1/2. The 2 and 1/2 cancel out. So then our integral is plus you multiply these together, minus you multiply these together, plus you multiply these together. So we're going to get x squared times 2 sine of x over 2. Grab the 2. Minus a minus, I'm going to get plus 2x times 4 cosine of x over 2. And then plus 2 times negative 8 sine of x over 2. From 0 to pi. So then we plug in pi, and we get pi squared times 2 times sine of pi over 2, which is 1, plus 2 times pi times 4, so that's 8 pi, times cosine of pi over 2, which is 0, and then minus 16 times sine of pi over 2, which is 1, minus, then we plug in 0, you get 0 plus sine of 0 is 0. So our answer ends up being 2 pi squared minus 16. Interesting. The point I'm trying to make with this problem is that when you're doing integration by parts, it's usually a good idea to do the integral first and then at the end plug in your limits of integration. Let me show you one more example of that. And a little bit easier example. Didn't mean for that one to be quite as difficult as it is. Sorry. So let's say I want to find, say, the integral from 1 to e squared of x squared natural log of x dx. I really don't, so here's my issue. I don't want to write this out as uv evaluated from 1 to e minus the integral from 1 to e of x of, whatever my vd is. I find this notation to be not nice. So here's what I would encourage you all to do. I'm going to do my integration by parts. I'm going to let u equal the natural log of x. Du is going to be 1 over x dx. dv is going to be x squared. I feel like we did this problem already. It's all right. And we did it with not linear integration. And v is going to be x cubed over 3. So then when I do the integral, I'm just going to do the integral of x squared natural log of x as an indefinite integral. And I'm going to get natural log of x times x cubed over 3 minus the integral of v du, which is x cubed over 3 times 1 over x dx. All right, so then I'm going to simplify this. This is going to equal the natural log of x times x cubed over 3 minus 1/3 times the integral of x squared, which is then going to be the natural log of x times x cubed over 3 minus 1/3 times x cubed over 3. So then we can go back to our original problem and be like, okay, this is then going to equal that. So the natural log of x times x cubed over 3 minus x cubed over 9 evaluated from 1 to e squared. So you can plug in e squared and you get the natural log of e squared times e squared cubed over 3 minus e squared cubed over 9 minus, plug in 1, natural log of 1 is 0. So that part's 0. So 0 minus 1/9. To me, that feels just a little bit less terrible than like having to do this. The integral from 0 to 1, sorry, from, but you could also do this. 1 to e squared, and then it's 1 to e squared, 1 to e squared. And you just keep like, and then at the end, you go, right? I mean, it's not like the worst thing ever. It just feels a little bit cumbersome to me. So maybe that's more of a personal opinion. That's what you get when someone teaches a class, you get their personal opinions about math. The better way to do things, hopefully. So I would encourage you, when you have an integral that looks like it's going to be integration by parts and it's a definite integral, I would say do the indefinite integral and then go back and be like, okay, now I'm going to quite learn some integration. Let's talk about odd and even functions for a minute. And I will be perfectly frank, I don't remember if we talked about odd or even functions in this class. I know I've talked about it in either this class or my 20B class. So if some of this is repetition, it's okay. It's good to see things more than once. So here's what we've got. F of x is odd if f of negative x is equal to negative f of x. But I do think I asked you guys an odd or even question. Yeah, we have talked about odd or even. So I think I asked you an odd or even question on your quiz, which is not the best question I've ever asked. There was kind of an error on it. Right, I'm confused by constant for sure. Let's just look at an example. So an example of this is f of x equals x cubed. It looks like this. And the thing to see is that whatever positive value you plug in, so like for example, you plug in 1, f of 1 is 1. And f of negative 1 is negative 1. And f of 2 is 8. And f of negative 2 is negative 8. And more generally, f of negative x is equal to negative f of x. And that's what it means to be odd. Negative x equals negative f of x. And you can also kind of see that, for example, if I pick some like a value here, it's a negative a value here, the area here and the area here, they're going to cancel out. So that if your function is odd, the integral from negative a to a of an odd function is going to be 0. Great. On the other hand, there are also even functions. So I will say, as far as integration is concerned, the odd function criteria is a lot more useful. The even function thing is still useful, but not quite as much. So let's say, so we know that f of x is even if f of negative x equals f of x. Classic example, f of x equal to x squared. You can see that no matter what x value you plug in, right, if you plug in, say, 1, you get 1. If you plug in negative 1, you also get 1. Well, that's true for anything, right? F of negative 2 is going to be equal to 4, which is equal to f of 2. And in this case, yeah, f of negative x is definitely equal to f of x. And if you want to pick some other value like a, let's say, right, here's a, and here's negative a. So notably, this symmetry here means that this area here on the right is equal to this area here on the left. So that you can make your life a little bit easier if you wanted to find the integral from negative a to a of f of x. You can instead say, well, I'm just going to do the integral from 0 to a. And double it. And that's if your function is even. So why do we care about this? Well, then we can ask some sorts of questions like, for example, let's see, where's my example here? Sure, we can look at both of these. Let's look at this first one. Yeah. So we can ask questions like, okay, given f of x is an odd function, g of x is an even function. And we're also going to be given that the integral from 1 to 3 of f of x is equal to 5. And the integral from 0 to 5 of g of x is equal to 7. First question, what's the integral from negative 3 to negative 1 of f of x? So we're just going to use the even odd property of the odd property of x, meaning, well, I'm going to draw a picture. So I know that f of x is odd, meaning if there's symmetry, right? It might look, and I don't know exactly what it looks like. I'm just going to make something up. It might look like this, right? Where this and this are symmetrical if you rotate about the origin. And so I know that the integral from 1 to 3, I know that this area there, according to what's been given to me, that's equal to 5. But then this region here should be the same, except it's under the x-axis. So that area there from negative 3 to negative 1, that should be what? Negative 5. Another way you could say it, if you really wanted to, is that the integral from negative 3 to 3 of f of x should be 0. And then you can break that up as the integral from negative 3 to negative 1 plus the integral from -1 to 1 plus the integral from 1 to 3. And that's equal to 0. You know that this is 0 because it's odd. You know that this is 5 because it's given. So that has to be -5 to make it work out. Okay. Let's look at a couple more odd or even things. Sure. What if I wanted to do, what if I want more room? I want to find, sorry, I'm kind of out of room here. I want to find 3 times the integral, sorry, not 3 times the integral. The integral of -5 to 5 of 6 times g of x. Well, again, I'm just going to use the even property of g of x. I'm also going to use the constant multiple property where you can bring that 6 out in front. So 6 times the integral from -5 to 5 of g of x dx. But then I can say, oh, g of x is even. So this is going to equal 6 times 2 times the integral from 0 to 5 of g of x dx. But we know what integral from 0 to 5 of g of x is. It's 7. So this is equal to 6 times 2 times 7, which is something. It's 84, I think. So that's kind of the idea with questions like these, is they're going to give you some information and then they're going to ask you to calculate stuff. Let's look at another problem. These are some properties from the book, and they're some problems from the book, and they're pretty similar to the practice. So we're given, and so this is something you actually could calculate, but we're given that the integral from 0 to 4 of x cubed dx equals 64. And we know that x cubed is an odd function. We could even draw a picture. So we know that the integral from 0 to 4, right, we know that that area is 64. Great. So automatically, here's what, before I do anything else, I'm going to say, well, I know that over here from -4, I know that this area is going to be -64 because it's the opposite of that. So I know before I even get asked a question, that the integral from -4 to 0 of x cubed dx has to equal -64 because it's an odd function. And let me double check. That's the first question they asked me. So -4 to 0 of x cubed dx is -64. And then if they ask me what the integral from -4 to 4 is, you could break it up, right? You could say, well, it's going to be, I mean, you could just say it's 0, right? Because it's an odd function. Or you could say it's the integral from -4 to 0 x cubed dx plus the integral from 0 to 4 x cubed dx, which is -64 plus 64. 0. But really, it's more that we used this part to answer the first question, right? We know this is true because, right, this plus this, which is 64, has to equal 0. So this has to equal -64. So that's how you would answer questions like that. All right. Time's up. That's not. We got lots of time. Let's go. Let's continue on. So more integration by parts. So let's revisit the tabular method. Slash the vertical method. So let's look at something like, what do we got here? Sure, let's look at the integral of x squared sine of 3x. And again, let's do this one the long way. We're going to do integration by parts. So I'm going to first let u equal x squared, and then dv gets to be sine of 3x dx. Right? This is I'm making the choice because I'm letting u be the thing that's going to get simpler when to differentiate, and then dv be the thing that's not terrible to anti-differentiate. It doesn't get more complicated. Derivative of u is going to be 2x. The antiderivative of sine of 3x is going to be negative cosine of 3x divided by 3. Okay. So then this is going to equal u times v. So x squared times negative cosine of 3x over 3 minus the integral of v du, which is going to be the integral of negative cosine of 3x all over 3 times 2x. Oh, I forgot the dx here. Now, I personally think you want to simplify this a little bit before you move on. This is going to equal, I'm going to write this as, how do I write that? Yeah, negative, let's do this as, okay, fine. Negative 1/3 x squared times cosine of 3x. That's not really the part I'm concerned about. What I'm concerned about here is I've got a negative 2/3. Write this as positive 2/3 integral of x times cosine of 3x. But now I need to do integration of parts again. So for this integral here, I'm going to let u equal x. du is going to be 1 times dx. dv is the rest, which is again cosine of 3x. Sorry, not again. It wasn't sine of 3x before. Cosine of 3x dx. And v is going to be 1/3 sine of 3x. So that when we integrate this thing, we're going to get, this is going to be equal to, I still have a negative 1/3 x squared cosine of 3x plus 2/3 times the entire integral, right, of x cosine of 3x. So, right, the integral of this is uv minus the integral of v du. So we're going to get 2/3 times uv, which is x times 1/3 sine 3x, minus the integral of v du. Meaning that 2/3 is going to have to distribute. So we're going to get negative 1/3 x squared cosine of 3x plus 2/3 times 1/3 is 2/9 x times sine of 3x. And then we're going to anti-differentiate. So we're going to get then plus 2/3 times the negative integral of this. So we're going to get negative antiderivative of 1/3 sine of 3x is 1/3 negative cosine of 3x plus c. And then this part here you should simplify as 2/27. Right, so this is really, I don't want to write it all again, but I guess I will. This is negative 1/3 x squared cosine of 3x plus 2/9 x times sine of 3x. Minus and minus is plus 2 on the top, 27 on the bottom, cosine of 3x. Not particularly fun. Yeah, Marshall, for sure. I was definitely, yes, that's on the agenda for today. But I do want to point out, right, this one you could also do via the tabular method. So I really want to emphasize, if you're allowed to use tabular, which again, some professors are like, don't use tabular because you haven't learned it in class or something, but it's a perfectly good method for this type of integral. Right, if I let u be the x squared and the derivatives are 2x and 2 and 0, and dv was sine of 3x, the antiderivative of that is negative cosine of 3x over 3. The antiderivative of that is negative sine of 3x divided by another 3, so over 9. And the antiderivative of that is cosine of 3x divided by 27. This times this, this times this, this times this. So we get positive x squared times negative cosine of 3x over 3 minus 2x times negative sine of 3x over 9, and then positive 2 times cosine of 3x over 27, which is totally negative 1/3 x squared negative 1/3 x squared times cosine of 3x plus 2/9 x times sine of 3x plus 2/27 cosine of 3x, which is exactly what we had over here. So totally works. Totally works for nice power of x times either sine or cosine or e to the x, or those types of functions. It doesn't work for anything else. So you cannot use the tabular if there's a logarithm. You can't use the tabular for like e to the x times sine of x. It only works for those 3 types of integrals. Yeah, let's go ahead and let's go ahead and look at another problem. So I'll do 2 of these at least. I'll make the first one not super gross. So I want to find the integral of e to the 2x times sine of x dx. For integrals like this specifically, where it's e to the something times sine or cosine, there's this process where you have to do integration by parts twice, and then something kind of special happens. So again, I've got an exponential and a trig. So according to the rate, I'm going to let u equal the trig thing. I will mention, for this particular example, it actually doesn't matter which way you choose it. You could let u equal the exponential thing as well. That would be perfectly fine. The thing you want to do for this, and that is vital, is you have to make the same choice for both times you do integration by parts. I'm going to make the usual choice because that's what I do. So I'm going to let u equal sine of x. Du is going to be cosine of x dx. dv is going to be e to the 2x dx. And v is going to be e to the 2x divided by 2. So then, this is going to equal uv, so it's going to be sine of x times e to the 2x over 2 minus the integral of v du, which is e to the 2x over 2 times cosine of x dx. And I would simplify this a tiny bit. I would say that this is equal to 1/2 sine of x times e to the 2x minus 1/2 the integral of e to the 2x times cosine of x. Okay, and now for this integral, I'm going to do the same sort of integration by parts. I'm going to let u equal cosine of x. Du is going to be negative sine of x dx. dv is going to be e to the 2x again, and v is going to be 1/2 e to the 2x, or e to the 2x over 2. So then we're going to get that this is equal to 1/2 sine of x times e to the 2x minus 1/2 times the integral of this, which is going to be uv. So it's going to be, let's write it as 1/2 e to the 2x times cosine of x minus the integral of v du, which is 1/2 e to the 2x times negative sine of x dx. Okay, let's simplify a little bit. We're going to run out of room here. Might run out of room here. So let me go up to the, fine. So here's what we've got, right? This is all what this integral is equal to. So we've got this integral, the integral of e to the 2x times sine of x dx equal to, let's see, I've got 1/2 sine of x times e to the 2x Simplifying this a little bit, it's going to be a -1/4 times cosine of x times e to the 2x. And then this times this is going to give me a minus times a minus times a minus. So it's going to be a minus 1/2 times 1/2 is 1/4. The integral of e to the 2x times sine of x. So look, I did integration my parts twice, and I got back to where I started. This integral here is the same as this integral here. So what I'm going to do, I'm going to add all of this over there. So I'm going to add 1/4 of the integral of e to the 2x sine of x dx. So when I do that, I'm going to get 5/4 of the integral of e to the 2x times sine of x dx equals this part right here. 1/2 sine of x e to the 2x. I'll just try to do this. E to the 2x sine of x minus 1/4 e to the 2x cosine of x. And then finally, multiply both sides by 4/5. I'm just going to write it up here since I'm out of room. So I multiply this by 4/5, I just get the integral of e to the 2x sine of x. And it's going to equal 4/5 times it. So 4/5 times 1/2 e to the 2x sine of x minus 1/4 e to the 2x cosine of x plus c. Questions about this one? No, definitely not. So someone asked, do you think situation would arise in which we'd have to do an antiderivative more than twice to find the repeating integral? And no, for these, so these types of problems, and there's really only 3 of them, and I don't think you encountered the 3rd one in this class. Yeah. These types of problems where it's e to the something times either sine or cosine, you do it exactly twice. You do integration by parts exactly twice, and then you're going to have the same integral you started with show up again, maybe with some coefficient on it, and then you're going to add that to the other side, and then you're going to multiply both sides by the reciprocal of the coefficient. And that's kind of it. Let's do another one. Do we really need to do, I mean, I feel like one example is kind of enough here. I feel like maybe that's good. Oh, so, no, sorry, man. Let's look at a couple more examples of just integration by parts. Yeah, Lee's homework problem number 12. Yeah, his homework problem 12. Lee's homework problem 12 is exactly like this. The same sort of idea. It's exactly the same process what we just did. Let's look at some more examples here. I've got a couple more problems. Okay. Yeah, I can get this one. Let's say I wanted to do the integral of e to the 2x times sine of e to the 2x dx. Well, unlike the previous problem, this is much less terrible. I'm going to do a U-substitution. U is going to be e to the 2x. My du is going to be 2e to the 2x dx. So 1/2 du is going to be e to the 2x dx. And then we're going to, we're going to be good to go. Here's my 1/2 du. And sine of u. So it's really important. I can't stress enough. When you look at a problem, don't be like, oh, this looks like one of those terrible integration by parts problems. You don't know until you actually kind of think about, can I do a U-substitution? That should really, when you're looking at an integral, your first question to yourself, if it's not just like super obvious, like the integral of x cubed, you're like, okay, how to do that, right? But if it's not super obvious right off the bat, the first question you should ask yourself is, can we do a U-substitution? That is always going to be really the easiest method to apply
with some minor exceptions, like if there's a back sub or something. But most of the time, U-sub is like, great, I'm done, I'm happy, U-sub is awesome. And then if we can't do a U-sub, then we start exploring other options. Can we do integration by parts? Can we do one of the other methods we haven't learned yet? So integral sine of u is negative cosine of u. So we get negative 1/2 cosine of e to the 2x. And here's a more interesting problem. This one's a little bit challenging. This one's actually kind of, yeah. Well, this one looks, Okay. I feel like I'm not going to do this problem because this problem, I don't know. It feels harder than it needs to be. How much time do we have? Yeah, we can. So this one, I feel like you probably wouldn't see this, but it's still good to see things that are hard. Let's say we want to do the integral of cosine of natural log of x. Oh. This is it. So this problem really is the same as an e to the x times cosine of x problem. Let me show you something kind of funky before we do this problem, just so you can see why what's going to happen is going to happen. Let's pretend we thought this was U-sub. Let's try u equals natural log of x. So there's this thing you can do where, right, so du is 1 over x. That's not super helpful. Right, I guess I could solve for dx here and say dx equals x times du, and then I could solve this for x and say x equals e to the u. So you could totally rewrite this as the integral of dx is e to the u du, and cosine natural log of x is cosine of u. Oh, look, it's an e to the u times cosine of u problem. That's kind of funky. We're not going to do it that way, but it is equivalent to that sort of problem. So we're expecting an answer where we do the same sort of thing, where you have to do it twice and then get the same things from back there. So let's talk about how you could do this using integration by parts. It's kind of weird. You could let u, so if you're not sure what to do, and you're like, I don't see a good U-substitution, and right, you can totally do this with a U-sub, but it's not super obvious to do it that way. If you're not sure what to do and you think it might be integration by parts, one option that is always a valid option, although it feels kind of lame sometimes, is to let u equal the entire integral except for the dv part, except for the dx part. So the dv is equal to dx. Then v is x, and du here is the derivative of this. So it's going to be negative sine of natural log of x times 1 over x dx. Which you might think looks super wacky. I would agree. But look what happens. When we write this here, it ends up equaling uv minus the integral of v du. Now, I would point out, this is going to be, I would do the simplification right away. So when I just have x times negative, fine, I'll write it out. So you'd have x times negative sine of natural log of x times 1 over x dx. Well, look what happens. But first of all, the negatives multiply together to make it positive. So let's just make that a positive. And then x times 1 over x cancels out. So we're left with x times cosine of natural log of x plus the integral of sine of natural log of x. And sine and cosine are essentially the same function. I mean, they're not exactly the same, but they're pretty much the same. They're just shifted from each other. So if you see that you integrate cosine of natural log of x and you get sine of natural log of x, you should say to yourself, oh, I got essentially the same function back, meaning I should do this process again. And now we're going to let u equals sine of natural log of x. My du is going to be cosine of natural log of x times the derivative of natural log, which is 1 over x. My dv is going to be still dx, and my v is x. So then this is going to end up equaling, so that x times cosine of natural log of x, plus, now the integral of this is my uv, so x times sine of natural log of x, minus the integral of my v du. Now I am going to simplify this here. V du, the x times the 1 over x cancels, and you just get cosine of natural log of x dx. But look, now we're literally back to where we started. So we ended up getting that this integral is equal to x times cosine of natural log of x plus x times sine of natural log of x minus the integral of cosine of natural log of x dx. So then you add that there, right? So we're going to add one of these here, add here, these cancel, and so then you end up getting two of these, 2 integral of cosine of natural log of x dx equals this, x cosine of natural log of x plus x sine of natural log of x. And then we divide both sides by 2. Go on plus c, done. So the integral of cosine of natural log of x is 1/2 x cosine of natural log of x plus x sine natural log of x plus c. Kind of weird. I'd never seen that question before, or at least if I had, it's been a long time, I don't remember. All right, one more problem. So most of the time, if it's integration by parts, the late acronym will serve you well. Meaning, first you pick u to be a log thing, then you pick u to be a power of x, then you pick u to be a trig thing, and you almost never pick u to be an exponential, meaning e to the x, or 2 to the x, or 3 to the x. So that's typically how we pick what u is for integration by parts, right? Not for U-substitution. U-substitution is a totally different ball of wax. This problem, however, so while this is mostly always true, it is not always true. And here is a problem I feel like someone came up with just to prove that there is sometimes a different way of doing it. So we're going to do the integral of, what do we got here? X cubed, it's a bizarre problem. X cubed e to the x squared over x squared plus 1 squared. And I believe this is problem problem number 28 in section 6.2 of your textbook, if you care. So here's what we're going to do. We're going to let u equal, and this is kind of bizarre, it's going to equal x squared e to the x squared. How do you know to do that? No idea. I wouldn't know to do that. The only reason this kind of makes sense is that when you break this up, so you're breaking it up as x over x squared plus 1 squared times x squared e to the x squared. The only reason this might seem like a plausible choice is because then your choice for dv, right? If this is my u and this is my dv, dv is relatively straightforward to anti-differentiate. It still requires a U-substitution, which is kind of annoying. But right, if we let u equal x squared e to the x squared, then my du is terrible. I have to use the product rule. It's going to be 2x e to the x squared plus x squared times e to the x squared times 2x. Okay, that's already awful. My dv is going to be x over x squared plus 1 squared dx. And the antiderivative of that, let's do a u-sub on the other side of the board real quick. If I'm doing the integral of x over x squared plus 1 squared, I'm going to let u equal x squared plus 1. Du is 2x dx.
1/2 du is x dx. So this is 1/2 integral of du over u squared, which is 1/2 the integral of u to the minus 2, which is 1/2 u to the minus 1 over minus 1, which is negative 1/2 times 1 over u, which is negative 1/2 times 1 over x squared plus 1. Whew, that's a pain. So then that was my v, right? It was negative 1/2 times 1 over x squared plus 1. And so far this might look like this seems insane, but it works. So if you write, right, if you do the integral, it's going to be u times v. So it's going to be, I'm going to write it as x squared e to the x squared over 2 times x squared plus 1 with a negative out in front, minus the integral of v du. So first of all, the minus 1/2 comes out in front. Let's make it a positive 1/2. And then v times du, so the denominator is x squared plus 1. And the numerator, now in the numerator here, this is kind of the important part, I can factor out a 2x e to the x squared. When I factor out a 2x e to the x squared, you're left with a 1 plus x squared, which cancels that. So this is how this all works out. And then this integral you're left with, the integral of 2x e to the x squared, is something that's totally doable. It's a u sub again. The integral of 2x e to the x squared is just e to the x squared. So this is going to be negative x squared e to the x squared over 2 times x squared plus 1 plus 1/2. And again, the integral of 2x e to the x squared is just e to the x squared, because the derivative of e to the x squared is e to the x squared times 2x. Clearly, someone with too much time on their hands said, I'm going to make a problem where you don't just pick u equal to the log or the algebraic, where you pick u equal to something with an exponential thing in it.